Welcome to Basic Electronics. In the last class, we discussed a half-wave rectifier circuit and looked at the various waveforms, namely the input and output voltages, diode current and capacitor current. To help in visualizing the circuit operation, we will now look at an animation which mimics charging and discharging of the filter capacitor. The animation will help us to understand clearly the reason behind the ripple voltage at the output. We will also get to know which factors are responsible for the ripple voltage and therefore how to make it smaller. We will then take up a numerical example, work out expressions for the various quantities of interest and calculate those quantities for the given circuit. Okay, let us get started. Here is an animation and the component values can be set here. For example, R can be 100 or 150 or 200 ohms. C can be 1, 1.5 or 2 millifarads. Vm, the peak of the input voltage, can be 10 or 12 or 15, and V on for the diode can be either 0 or 0.7 volts. So let's compute, and when we compute, many things happen here. We will look at it soon. The ripple voltage VR is approximately 2, and we will look at this approximate way of calculating VR. And if you do it more exactly, it turns out to be 1.66 volts. Before we start the animation, let us note a few things. So there are two tanks here, one corresponding to the source and the other tank corresponding to the capacitor. And there is going to be water in these tanks, and that water level corresponds to the voltage, either the source voltage or the capacitor voltage, which is the same as the output voltage. Water flow is going to correspond to current. So there is going to be water flow out of this tank, there is going to be water flow into this tank, and that corresponds to current. Capacitance corresponds to the area of the tank. For example, if this tank was wider, then that means the capacitor is larger. And the capacitor charge is equivalent to the volume of the water inside. So if this tank has a certain volume of water, that corresponds to the charge on the capacitor. The flow rate out of the right tank, that is the flow rate over there, is equivalent to the load current through the resistor, which is approximately Vm by R, because we have seen that the voltage across the resistor, which is Vo, is nearly equal to Vm. Also, it's good to note this formula. Ripple voltage VR is given by Vm times T, the period of the input waveform, divided by RC. We are actually going to derive this formula soon. For a 50 Hertz input, the time period is 20 milliseconds. Also, since the diode resistance is very small, the charging process is instantaneous, as we have already remarked earlier. So with these in mind, let us now look at the animation. So what we will do is we will just let the animation run for some time and then comment on what's happening. So just observe for 2 cycles. So let us now relate what is happening in this picture to our actual circuit. So there is this source. It's like an artificial tank. There is no such tank in nature. And its water level goes up and down. It just keeps going up and down forever, just like the source here. This source tank is separated from the capacitor tank with a membrane or a wall. Now this wall is rectifying, so it allows water to flow from there to there, but not the other way, and that is the meaning of this arrow here, the same as this arrow, because the diode does not allow current in that direction. Let us now comment on the size of the currents involved, in particular the load current and the diode current. Where is the load current in this picture? The load current is right here. So the load current basically is responsible for discharging the capacitor here, and this water flow is responsible for emptying the tank, the capacitor tank. And that is a relatively slow process, because we don't want the level to drop drastically. We want the level to be in fact constant. Now what happens is this source level goes up, and when it goes above the capacitor level, then there is a sudden water flow from the source to the capacitor. And let's just watch it once again. So as we see, this process is going on continuously, and whatever water is lost from the capacitor tank has to be replenished from the source in a very short time, because it's only a short time that the water level in the source is higher than the capacitor level. So the water flow that happens in that short time must be much larger than this water flow, and that means that the peak diode current must be much larger than the average load current. Let us now try to understand the relationship between the ripple voltage, that is this difference here, and the capacitance value, the resistance value, and Vm, the input amplitude. Let's consider the capacitance first. Where is the capacitance in this picture? The capacitance is the volume of this tank. It represents the capacity. Now suppose we increase the capacitance from 1 to 2 millifarad. What would happen? The capacitance would then increase, the tank would increase in size. Now we have not really changed the resistance value, so the flow rate, which corresponds to the average load current, which is Vm by R, that is not changing, and therefore in a given time, that is in one period, the volume of the water that is lost from this tank would still be the same, but now the area of this tank has increased. So what it means is the height or the ripple that this situation corresponds to will now be lower. So let's check that out. So remember, the earlier ripple is 2, and now let's compute again. Now the new ripple voltage is 1, and as we expected, the size of this tank has increased. What if we increase the resistance value, let's say from 100 to 150? What would happen then? Now, as we have seen, the resistance controls this flow out of the capacitor tank, and it's given by approximately Vm by R. So if I increase the resistance, this flow is going to decrease, and in the same amount of time, that is one period, the volume of the water that is lost from this capacitor tank will then reduce, and we have to then replenish only a smaller volume, and that corresponds to a decrease in the ripple voltage. And let us check that out. R from 100 to 150. The ripple voltage with 100 is 2 volts, and with 150, let's compute, it is 1.33 volts, and that is what we expect. Okay, so let's look at this example, half wave rectifier with capacitor filter. We are given Vm to be 16 volts, frequency 50 Hertz. Of course, about this we don't have too much choice because that's the same as the mains frequency. R, the load resistor, is 100 ohms, and for a ripple voltage of 2 volts, we want to find the filter capacitance. So we'll do that first, and with that capacitance value, then we will look at what is the average and peak diode current, and what is the maximum reverse voltage that appears across the diode. And in all of these calculations, we will assume that V on is 0 volts, and in reality, different V on like 0.7 volts doesn't really make too much difference, and we have already seen that in the plots that we saw earlier. Okay, so let's begin with the A part, calculation of the filter capacitance. Let us recall that the diode conducts in a relatively small interval, then it is off, then again it conducts in the next cycle, and so on. This part corresponds to the charging, that is increase of voltage, and the maximum is Vm. And this part, this interval, which is marked as T2 here, from there to there, this corresponds to discharging of the capacitor through the resistor. So the diode is off, and because the capacitor is discharging through the resistor, we have this drop in the output voltage. At this point, once again the diode starts conducting, and the capacitor voltage, the output voltage, increases. Alright, so now that discharging process corresponding to this RC circuit with the diode off is described by this equation. Vo of t is Vm e raised to minus t by tau. Now tau normally is selected for a small ripple, and that happens if the time constant RC is much larger than 1 period. And if that is the situation, this t by tau is much less than 1, and then Vm e raised to minus t by tau can be approximated as Vm times 1 minus t by tau. Now at t equal to 0, our capacitor voltage is Vm. At t equal to T2, this is 0, this is T2. At t equal to T2, our capacitor voltage has dropped by Vr, that is our ripple voltage. So in other words, if we substitute t equal to T2 here, then Vm times T2 by tau should be equal to Vr. Now the problem is that T2 is not known, and this is where we make an approximation. That approximation is that T2 is nearly equal to T. So what we are saying is that T2 is nearly equal to the entire time period. Now this is not an unreasonable approximation, because the time during which the diode conducts is indeed small compared to the time period, and therefore this is a reasonable approximation. So with that approximation, we now get Vr is Vm
times T2 by tau. Now T2 is approximately T, so therefore VR is Vm T by tau, which is Vm T by RC. Here is another way of computing the ripple voltage. We start with IC equal to IR in the discharge phase. The diode is not conducting, and IC and IR are therefore equal in magnitude. IR is VO by R, and VO is approximately constant, which is equal to Vm, and that holds if the ripple voltage is small. So we have IC equal to Vm by R, and IC is also equal to C dVc dt, which is the same as C dVo dt, because VO appears across the capacitor as well. And if we look at VO in the discharge phase, it falls linearly, and we have seen the condition for that to happen, that is the time constant RC is much larger than the period T of the input waveform. So if VO is falling linearly, then the derivative is constant, and we can calculate the derivative by using delta VO divided by delta T, and that is written here. Delta VO is the same as VR, and delta T in the discharge phase is actually T2 if we come down, that is T2. And once again we will make this approximation that T2 is nearly equal to T, and therefore we get IC equal to Vm by R equal to C VR by T, and that gives us a value for VR. So VR is Vm T by RC. From this expression for VR, we can now obtain C. It's Vm by R times T by R, and we have been given these values, and we want to find C. So Vm is 16 volts, VR we require it to be 2 volts. The time period corresponds to the input frequency of 50 Hz, which is 20 milliseconds, and R, the load resistance, is 100 ohms. When we calculate this number, it turns out to be 1600 microfarads or 1.6 millifarad. Let us now look at the average diode current, and we can use charge conservation to obtain this. Charge conservation requires that the change in Q for the capacitor in one period must be 0. And since IC is dQ dt, we require the integral of IC over one period to be 0. So let's look at the capacitor current, which is shown here. Now in this interval marked TC here, the capacitor current is positive, the diode conducts, the capacitor gets charged like that. And in this second interval, the diode is not conducting, ID is 0, and we have only this R and C in parallel. Now the capacitor is supplying current to the resistor, so IC is negative. So we see that here, this is a negative current. And now charge conservation requires that the integral under this curve should be exactly equal and opposite to the integral of this curve, or the area under IC in that interval. So that is our starting point, and let us see what that implies. In the charging phase, ID is equal to IC plus IR, so therefore we can write IC as ID minus IR. And in the discharging phase, this ID is 0, and therefore IC is equal to minus IR. So let us now put it all together and obtain an equation which results from charge conservation. That is what we get. So this ID minus IR is nothing but IC in the charging phase, and therefore the limits here T minus Tc to T. What is T minus Tc? This is our 0. This is our T, this point. T minus Tc is this point right here. Okay, so T minus Tc to T is basically this interval marked here. What about 0 to T minus Tc? This is our 0 and 0 to T minus Tc. So we are talking about the discharge phase now. So these two integrals must be equal, and we can simplify things. We can club this integral IR dt with the one on the right hand side, and then we get integral ID dt, T minus Tc to T is integral IR dt from 0 to T. And now we want the average value of the diode current. What is the average value? It is simply the integral from 0 to T ID dt, and 0 to T essentially means T minus Tc to T, because the diode does not conduct in this other interval, and that we need to divide by the period T. So that is what we get, and since this and that are equal, we get ID average equal to 1 over T integral IR dt over 1 period. Now IR is nearly constant as we have seen before, so it's just Vm by R, and then so the average value of ID turns out to be equal to the average value of IR, that is Vm by R. And for this example, it turns out to be 16 volts by 100 ohms, that is R, and that is 160 milliamperes.
To summarize, we have used an animation based on the analogy between the half-wave rectifier and a hydraulic system. This analogy helped us to identify the factors responsible for a non-zero ripple voltage at the output. After that, we worked out an approximate formula for the ripple voltage and used it in a numerical example. In the next class, we will complete the half-wave rectifier problem and then take up the full wave rectifier circuit. Until then, goodbye.